Hi friends, we are going to discuss about the topic the helium atom. As we know that helium atom consists of a nucleus of charge Ze at the origin and two electrons with radius vectors r1 and r2 as shown in the figure. Neglecting the motion of the nucleus, the Hamiltonian of the system is H is equal to minus h cut square by 2m del 1 square minus Z square by 4 pi epsilon 0 r1 plus minus h cut square by 2m del 2 square minus Z square by 4 pi epsilon 0 r2 plus E square by 4 pi epsilon 0 r12. So we are taking this equation as equation A. Here, the del 1 and del 2 refers to the coordinates of electrons 1 and 2 respectively, and the term E square by 4 pi epsilon 0 R12 represents the electrostatic repulsion between the two electrons. So we can write H1 is equal to minus h cut square by 2m del 1 square minus Z square by 4 pi epsilon 0 r1 and H2 equals minus h cut square by 2m del 2 square minus Z square by 4 pi epsilon 0 r2. So we can rewrite the equation A as H is equal to H1 plus H2 plus E square by 4 pi epsilon 0 r12. The Schrodinger equation corresponding to H1 and H2 are exactly solvable and the solutions are simply hydrogenic wave function. So, minus h cut square by 2m del 1 square minus Z square by 4 pi epsilon 0 r1 into psi 10 equals E10 psi 10. The helium atom is an example of a system having more than one electron, and its ground state energy was discussed by the perturbation and the variation methods without considering the symmetry effects of the spin of electron. To illustrate the evaluation of the energy of the ground and the first excited states by considering the fact that electrons are identical fermions and therefore the total wave function must be antisymmetric. It is convenient to use the perturbation technique for the evaluation. All the terms except the last one in the Hamiltonian equation, which is our equation A, can be used as the unperturbed part with the product of hydrogenic wave function as unperturbed eigenfunction. That is psi 0 equals psi 10 psi 20 equals z cube by pi a0 cube exponential minus z r1 plus r2 by a0. So the unperturbed energy becomes E0 equals minus 2z square WH, that is minus 8 times 13.6 electron volt, which is minus 108.8 electron volt. And moving to the ground state of helium atom, the ground state of helium atom is the 1s2 state. We know that as both the electrons are in psi 100 state, psi 0 equals psi 100 psi 100 r1 psi 100 r2. Using the antisymmetric spin product function, the zeroth order helium wave function for the ground state is psi 0 equals psi 100 r1 psi 100 r2 1 by root 2 times alpha 1 beta 2 minus beta 1 alpha 2. As the Hamiltonian does not contain spin dependent terms, the energy is not affected by the inclusion of spin function. So this is about the ground state of helium atom. Now we are moving to the first excited state of helium atom. Here, the excited state of helium atom consists of one electron in the hydrogenic ground state and the other in the excited state. So, the wave function psi of r is equal to psi 100 psi NLM. The excitation of both the electrons need more energy than the ionization energy of the atom. Considering the first excited state, the possible electronic configurations are 1s2, 1s, 2s and 1s, 2p. Except for the electron exchange, the first one is non-degenerate and the second one is threefold degenerate. Since the electron in the p state has the possibilities m equals 0 or plus or minus 1. And here the exchange degeneracy doubles this number. So we shall consider only the 1s, 2s state. Here for applying perturbation method, the two unperturbed states are psi 1 0 0 R1, psi 2 0 0 R2 and psi 1 0 0 R2, psi 2 0 0 R1. Okay. So we can write the perturbation matrix as the form J, K and Kj, where J and K are the Coulomb energy or direct energy and exchange energy respectively, and these are given by J equals double integral psi star 100 R1 psi star 200 R2 e square by R12 psi 100 R1 psi 200 R2 d tau 1 d tau 2, and K equals double integral psi star 100 R1 psi star 200 R2 e square by R12 psi 100 R2 psi 200 R1 d tau 1 d tau 2. Here both the J and K are always positive, and the eigenvalues of the perturbation matrix can be obtained from the solution of the determinant. So we can write it as J minus E1 K and K J minus E1, which is equal to 0. Where we are taking this E1 is a first order correction of the energy. So from the solution of the determinant, we can write E1 equals J plus K and E1 is equal to J minus K. These energies correspond to the normalized eigenfunction. So psi plus equals 1 by root 2 psi 100 R1 psi 200 R2 plus psi 100 R2 psi 200 R1, and psi minus equals 1 by root 2 psi 100 R1 psi 200 R2 minus psi 100 R1 psi 200 R1 respectively. The energy of the singlet ES and the triplet ET states corrected to the first order are ES equals minus 2 Z square WH plus J plus K and ET equals minus 2 Z square WH plus J plus K. J minus K. Here a simple interpretation of the Coulomb energy follows, and it can be written as J equals double integral modulus psi 100 R1 square modulus psi 200 R2 square e square by R12 d tau 1 d tau 2. And we can see a graph here, and it indicates the variation of modulus psi minus square and modulus psi plus square against R1 minus R2. From this we can understand that the dip in the probability density modulus psi minus square curve around R1 is approximately equal to R2, and it is called the Fermi Hole, and the increase in modulus psi plus square in the same region is called Fermi heap. The state described by the singlet is often referred to as parahelium and the triplet state as Orthohelium. The orthohelium has somewhat lower energy than that of the perihelium, which has been verified experimentally. The ground state is obviously perihelium, whereas the excited states come in both forms. So, this is about the topic, the helium atom. Thank you.